In this video I'm going to show you, I'm going to actually extend a specific program that I've done before, just to show you how I'm changing the program that will be able to help me to change the frequency if there's a different frequency needed. So I'm going to go back to my program that I've written. In the previous video where I have shown that if I want to have a change or want to know what the formula can be if the frequency is also not known, I will use this. Let me rather go to this one first. This is the formula that we will be using to calculate the time high. If the frequency is not known, I'll be able to change the frequency. Well, the program will be able to change the frequency, and of course the ADC output will then change the duty cycle. So this is the formula for the time high. This is the start point if the time high, if there's a time low. This is the ADC, and that again is the frequency, which will be unknown. So in my program, if you look at my previous program, I'm just going to scroll slowly through this, so that if you let me first just scroll through this, then if you want to copy the program, you can still copy the program. That should be able to help you to get hold of the program. So let me just scroll through this right to the end. Okay, so there you've got the program that I've written to do pulse width modulation with a frequency that is not known, and also with an ADC that's changing. So if I can just quickly again read through this program, as I've said here, this is just a start point. This is just any start point for my timer, just an initial start point. It's not going to make any difference if I don't even put this in there. It's actually irrelevant. Here I've selected the ADC to be below 200 kilohertz. I've selected ADmax to be 40. That selects a VCC or VREF as the 5 volt. It's right justified. But the section I really want to go to, because I've explained all of this before, again, just to make sure, because I'm doing a simulation here, I have started off by saying my variable low is 29 hex and a variable high is 1, which means I'm just taking with the assumption that my ADC out is 297, and as I've seen before, we've calculated that if it's a 10 kilohertz signal, then 297 actually indicates 29% duty cycle. So once you complete or implement this program, of course, the comments must be removed here, and the comments can be placed before this low. Those comments should be removed, and the comments should be placed before that high. So that's your final product. Because you have to multiply with a high value here, I had to make use of a double, because this value, if you multiply it, it's more than 4 million, and then the only value that can basically accommodate that would be a double. So if I just quickly look back at the formula, if you look at this formula that I've basically derived here, it's this one, the ADC divided by F multiplied by 15640 there. You can see in my program, this is the one multiplied by 15460, and what I wanted to say is this one here. Yes, this high here is basically, you will see if you look back in my program, that is what this is the combined value from the received from the ADC. So that's actually the ADC. This high is actually equal to the ADC in the Word document, whereas this for frequency here, you can see I'm actually implementing that frequency, And then what I've decided, what I've done in the beginning of the program, I have said I am defining freak, in my case, as 10,000. So if I want to have a 10,000, a 10 kilohertz, which is a 10,000 hertz, then I would place 10,000 in here. If I want my frequency to be 20,000 or 5,000, I would come and make the change here. So of course your pulse width modulation will only be for a specific frequency. So you'll change it once and then it's applicable to that specific frequency. It can be programmed into your application and it will work perfectly. Good. So, and you will see then that this formula that I'm using here is basically exactly, if you combine all of this, that is my formula for high, which is this one here, and my formula for low, which is actually this formula here. The start point for the low is that one, and if you look at my program, this is where I have implemented the low value. So for now, let's just quickly have a look at this. If the frequency is 10 kilohertz, then basically we know by now that it should be high for 29 microseconds and it should be low for 71 microseconds. So if I can quickly just do a debugging here, I can just show you again that my formula is working. Let me just step here, let's step one more time, let me just reset the stopwatch here, and if I now run, you will see that my high time was actually 31 microseconds, which is a little bit higher than what it's supposed to be. It's supposed to be 29 microseconds, but you can make small changes in the program, or not the program, in the formula in the program, which will bring it closer to 29 microseconds, making it a lot more accurate. Just want to add this. Yeah. And if I tell this thing to run again, you'll see that the total time is now 104, but unfortunately, let me rather do this. Let it run again. Let me just reset this and let it run again, and you'll see if it runs now, the status was 0, indicating this thing is at the low condition, and it did that for 72.94 microseconds. It was supposed to be 71 microseconds, but again, a slight error in there, and you can fix that error yourself if you really want to, and to get it more accurate. So if I go back, let me just get out of debugging here. If I go back and I want to change this now to become 20 kilohertz, just to show you that the frequency can be changed. If I go to my calculator, then it actually works out that 1 divided by 20 kilohertz, exponent 3, my duty cycle becomes 50 microseconds. Sorry, not my duty cycle, my period becomes 50 microseconds if the frequency is 20 kilohertz, which means if I multiply that by 0.29, because this value that I'm using here of hex 129 is still indicating a 29%. That didn't change. It's still indicating that. That means it must be a high time of 14.5. So just by changing, and of course then the load time should be in the order of 35.5. If I'm changing, just by changing the frequency here in the beginning of the program, let me just build this, and there's build succeed, and I can go now and see how close do I get to 14.5. Let me just run this, and then I will basically reset this. Let's just run now, and you'll see I get to 16.5 microseconds. So it is 2 microseconds out on the high time. Let me just reset this again, and let me run again, and it is 37.5 microseconds out on the load time, meaning that there's also a 2 microseconds problem there. So, but yes, again, as I've said, in the program you can just go and change. If you really want to get it more accurate, you can change in this formula here to make sure that this thing becomes a lot more accurate. So by just changing in your formula here, it is possible to accomplish that. So this is the way how I have written my program to make or to change the program so that I can also have this program used for any frequency changes that are needed. And as I've said, the ADC, that's basically indicating what the duty cycle must be. I hope you enjoyed this video. We'll talk again at some point. Thank you.